Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later from our college, I get to know about XLR and I enrolled in XLR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good teacher. He's not only focusing on theory part, he's doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they're also conducting different exam to test our knowledge, and as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, XLR.
Recently, I was searching for digital marketing courses online in Google, and I came across XLR, and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped, so I came to the XLR office in Bengaluru. This digital marketing course has helped my career and my skills to develop, and the certificate has helped my
Good evening, all. I hope you all doing well. We will start the session. Good evening, Adil sir. Is I'm audible? Adil sir, you are there?
Yeah, good evening. Good evening.
Yeah, good evening, sir. You can take over the class for the day.
Okay, fine.
Yeah.
Yeah, good evening, everyone. Hope you are doing great. Good evening. Okay, let me share the screen first. Yeah. Hope it is visible, right? Just
Yes, sir, it is visible. Yeah.
Okay, fine. Thank you for confirmation. Yeah. Yeah, if you know, yesterday we discussed so many topics related to computer science, related to algorithms, related to programming. So it was, I guess, performance analysis. Yeah, let us recap it within 2-3 minutes. We just recap what we discussed yesterday. So it was performance analysis. Means we were just discussing about the time and space complexity of programs, time and space complexity of algorithms. And if you remember, we discussed about first thing about space complexity. It was simply the amount of computer memory a program is taking to run to its completion. Then we discussed some use cases, examples. Like it was simply we were taking into consideration how many variables are there in the program. So we're supposing that each variable is taking some kind of a memory, and we were just saying that this is the space complexity of that program, right? Similarly, after that, we discussed something about time complexity, and time complexity was simply the amount of computer time a program is taking to run to its completion. Then we discuss some examples of time complexity, because initially I told you there are so many calculation a program is taking, but we are not calculating the actual time. We are not computing the actual time these calculations are taking, because it is a cumbersome process. We can have a transaction, banking transaction, or a banking statement, or any kind of a banking calculation that is taking huge number of calculation. Means there are tremendous number of additions, tremendous number of subtractions, multiplications, divisions, and other operations. So to compute, to have a track of each and every calculation, it is very difficult. And then we have to compute what each addition is taking, what each multiplication, the time by each multiplication, the time by each division, etc., etc. So it is totally, I can say, cumbersome process. So that's why we didn't go that way. Then we discuss about then what is the way to compute actually or to calculate the time complexity of an algorithm. So it was simply a step count. We were just calculating the number of steps an algorithm or a program is taking. Then we discuss so many algorithms like addition, matrix addition, recursive sum. So then we compute what? Then we compute the step count. If you remember, initially it was like n plus 3, tr sum, etc., etc. So we discussed so many algorithms where we computed what? This step count, or I can say the time complexity, right? So it was actually in terms of a function, right? Yes. Then after that, if it is in terms of a function, then we discuss about the asymptotic notations. Like if you remember, I told you that whenever you have to calculate something, if it is a length, then there should be some metric. For example, in meter, centimeter. Similarly, if you have got a weight, you have to weight. It can be in grams, kilograms, etc., etc. Similarly, if you want to check the performance of an algorithm, there should be some measure. So whenever we are measuring the complexity, the performance of any algorithm, of any program, so there should be some measure, and that measure is asymptotic notation, right? So it is simply a measure by which we are computing the efficiency of an algorithm. If you remember, yesterday we discussed 3 asymptotic notation. Although there are 5 asymptotic notation like big O, big omega, theta, little o, and little omega. But we discussed main 3: big O, big omega, and big theta. And if you remember, we discussed big O is worst case, upper bound, then omega is best case, lower bound. Similarly, theta is the average case. We discussed some examples, etc., etc. Right? If you check over here, hope my screen is visible to all of you. Yeah. If you check, see here, these are some of the complexities, and in most of the exams you will be like, I can say, just a minute, yes, you will be getting some of the functions, right? And you will be asked to arrange those functions in the order of their asymptotic growth. Hope you got the question. Again, I am repeating, you will be given some functions and you will be asked to arrange these functions either in increasing order of their growth or the decreasing order of their growth. So there are some functions. If you check, see, this is big O, this is the linear function, and it is not affected by the input side because it is constant. If you check that calculation yesterday, the basic program that was having some numerical calculations, a b c, a plus b plus c, a divided by c, etc., etc. So that was constant. Then we have got logarithmic notation, order of log n. Can anyone tell me for which algorithm the complexity is log n? Yes. Any algorithm for which the complexity is log n? You have to be very quick with your answers, please. Okay. If you see, it is written over here. It is actually binary search. We will discuss it later what binary search actually is and how is the complexity log n. Then we have got linear. Can anyone tell me any example of an algorithm for which the complexity is order of n? Yes. Any algorithm for which the complexity is order of n? Any example? Just write in the chat box. Any example of a program or algorithm for which the complexity is of the order of n? Yes. It is linear search. Good. See, yesterday we discussed it. If you remember, I was having a list of elements 1, 2, 3, 4, 5, and so on. Then I told you to search an element. And whenever the element is at the last or the element is not found in the list, then we have to check n times. So it means the complexity is of the order of n for this n number of elements or the input if the input size is n. Similarly, we have linear arithmetic means n log n. It can be a merge sort, heap sort. We'll be discussing all this, how it is of the order of this. Then you can have a polynomial complexity as well, or you can have exponential complexity, or you can have factorial complexity. So we'll be checking all these. If we see the order of their growth, right? See, increasing order of the complexity, it means this factorial is having highest order and the constant is having the least order. So this is the actual order of their growth. You have to check it and you have to remember it, right? Yeah, this is actually the graph. If we see, these are again some functions. See here, actually we did it. If you remember, this is the factorial. It is having the highest order as among all these functions. We have got logarithmic function, root function, linear arithmetic, polynomial function, cubic function, quadratic, exponential. But among all these functions that you are seeing in this graph, the factorial is having the highest order. Similarly, this 3 raised power x, 2 raised power x, x cube, and so on. क्या नहीं समझ आया? एक बार फिर समझा दो. Can you repeat what you want to learn? What you want to repeat? See, I am just saying that you have got so many functions and you will be asked to arrange those functions in the order of their growth, right? And you have to check, you have to keep in mind what is the actual order of the growth of the functions. If you see here, see, this is actually the order of the growth. Constant function, you can have logarithmic function, you can have linear arithmetic, polynomial, exponential, or factorial. Among all these functions, this factorial function is having the highest order, or I can say it is the highest complexity among all these functions, factorial. Similarly, exponential and polynomial, right? And if we see the graphs, this is the logarithmic graph, this is the root graph, this is the linear graph, linear arithmetic, polynomial, etc. etc. Among all these functions, this x factorial is having the highest growth, right? So this is actually the factorial function that is having the highest growth. Now there is a question. You just take a screenshot of it, and it is an assignment to you. Not assignment, it is a kind of a task. You have to arrange all these functions in the increasing order of their growth. Take a screenshot, and definitely there would be questions asked from this set. There are almost 15-16 functions, right? Take a screenshot of it and arrange these functions in the increasing order of their group. Definitely you will find some questions among this in competitive exams, and make sure you will understand why this is like this and why this function is increasing like this. Okay, hope you have taken the screenshot. Yes or no? Okay, fine. Yeah, see, now the next topic is recurrence relation. If you remember, yesterday we computed the step count of algorithms, right? That was not a kind of a number, but that was in terms of a function, right? So actually, whenever you are computing the complexity of an algorithm, so you will compute the complexity in terms of a function, and that function can be then evaluated with the help of asymptotic notation, and you can compute the complexity of that algorithm in terms of big O, theta, or big omega, right? Now, what if there are some, I can say, algorithms for which the complexity is in terms of a relation, and that relation is called a recurrence relation. See, it is actually a mathematical expression that is defined in terms of its previous terms. Can anyone tell me just quickly any example of a recurrence relation? Yes, quickly. Example, recurrence relation is simply a relation which is defined in terms of its previous terms. Yesterday we did one example. We did one algorithm, recursive algorithm. For that recursive algorithm, we can write a recurrence relation. Yes, Fibonacci. Good. Fibonacci series. Great. See, if I write a recurrence relation for a Fibonacci series, how is Fibonacci series recurrence relation for a Fibonacci series represented? If you know, nth term in Fibonacci series is equivalent to sum of its previous two terms. So it is f of n minus 1 plus f of n minus 2. So this is actually recurrence relation, because as I already defined, a recurrence relation is a relation or a mathematical expression in which any nth term is represented in terms of its previous terms. Right? So nth term in Fibonacci series Fn, it is represented as the sum of its previous two terms. For example, if you have to find the fifth number in Fibonacci series, what it would be equal to? It would be equivalent to fourth number plus, yes, plus third number. So then you have to compute the fourth number and the third number. Similarly, then you have to go for the fourth number. Fourth is equivalent to third plus second. Then third would be equivalent to, yes, second plus first. And this is the base condition. If you remember, for any recursive algorithm, for any recurrence relation, you will be given a base condition. Right? And if you remember, what are the first two numbers for a recurrence relation? Just write down. First two numbers for a recurrence relation. Great. It is 0 and 1. Right? So it will be like third number would be equivalent to, see, it is actually, I am just showing you how to calculate it. Third would be equivalent to 0 plus 1, that would be equivalent to 1. Similarly, fourth would be equivalent to third plus second. So it would be 1 plus 1, that is equivalent to 2. Similarly, then fifth number would be equivalent to what? Fourth plus third, that is 2 plus 1, that is equivalent to 3. So you can say the fifth number in Fibonacci series is equivalent to 3. Right? So this is how these recurrences are written. So a recurrence relation is simply a relation, a mathematical expression in which nth term is equal to the sum of previous terms. It can be any mathematical. It is not always the sum of previous two terms. It depends upon the problem. If you remember, there is a famous problem in algorithm that is called as Tower of Hanoi. Has anyone any idea? We'll be discussing that because that is also important. See, there are some examples. First, let me ask you the question. Fibonacci. This Tower of Hanoi. Anyone? What is Tower of Hanoi? I'm clearing my drawing. Tower of Hanoi. And that Tower of Hanoi is also solved with the help of recurrence relation. Arrangement of disks. Great. Move disks from source to destination. Nice. Okay, we'll be discussing arranging 3 disks. There are any number of disks up to 64. Okay, great to see your answers. See here. This is the recurrence for Fibonacci that we discussed. Then there is a factorial of a number. See, factorial is also equal to, if you have to find the 6 factorial. What is 6 factorial equal to? It is equivalent to, yes, Simply 6 into 5 factorial, isn't it? So recursively, we will be computing the factorials. Then you have 5 factorial in turn equivalent to 5 into 4 factorial till you will reach the base condition. And what is the base condition for factorial? 1 factorial is equivalent to what? It is equivalent to 1, and 0 factorial is actually equivalent to 1. So this is actually the base condition for factorial. 0 factorial is equivalent to 1. Until then, you have to make use of recursion. You have to make use of stack in order to compute this n factorial. So for Fibonacci, fn is equivalent to fn minus 1 plus fn minus 2. For factorial, it is equivalent to n into f of n minus 1. Right? N factorial into n minus 1. N into n minus 1 factorial. Right? Then there is another algorithm, and that is merge sort. And this is the recurrence relation for merge sort. And how to solve these recurrences, I will show you. There is substitution method, there is iterative method, there is iterative tree recursive method, and there is one important method that is called as a master theorem. And from master theorem, you will find at least 1 or 2 questions in the GATE exam as well. So this is actually a master theorem, a case of a master theorem, and it is, I will explain what is this 2, what is this 2, what is order of n. So these are actually, it is represented in terms of a recurrence relation. Then another example is Tower of Hanoi. See here, this is Tower of Hanoi, and it is the recurrence relation for Tower of Hanoi. I will explain after this what Tower of Hanoi is, and this recurrence master method as well. Our today's session would be around this. Then there is one more algorithm that is called as binary search, and this is the recurrence relation for binary search. Hope it is clear. And how it is, I will show you. Actually, it is ATN by B plus F of n, where A is the number of subproblems and this B is the size of each subproblem, etc. I will let you know actually the whole thing about these recurrences. Hope it is clear until now. Yes. Is it fine, or you have any questions till now? Java, we are actually going to the Java classes, because before Java, we have to clear the concepts of DSA. DSA means data structures and algorithms. Once you have these concepts clear, only then you can write binary search, merge sort, quick sort, insertion sort. In the Java is simply a platform, programming language. And once you have these DSA concepts clear, you can write the program that we'll be doing in coming lectures. But for that, our basics should be very much clear related to algorithms. And this is more important as compared to that programming part. Programming part you can do. If you have a logic, you can write a program, but logic is main thing. Yes, I will explain this merge sort recurrence relation. Okay, so it is clear. These are actually recurrence relations of these examples like Fibonacci, factorial, merge sort, Tower of Hanoi, and binary search. Now there is one question about how to solve these recurrence relations. Right, there are multiple methods by which you can solve the recurrence relation, and here we'll be using the master method. We can have substitution method, you can have recurrence tree method, you can have master method. Right, substitution method, if I will tell you these recurrences, the recurrences of this Tower of Hanoi, we can solve it using the substitution method. Fibonacci series can also be solved using I guess this substitution method or iterative method. Right, now there is one important method, we call that as a master method or master theorem. With the help of this master theorem or master method, we are actually doing what? We are solving the recurrence relation, but only a particular case of a recurrence relation. Not all recurrence relations are solved by master method. Like I told you about Tower of Hanoi. We can't solve Tower of Hanoi using master method. We have to use the iterative method. Right? Similarly, there might be a recurrence relation that is not of the form of this, the form which master method is solving. So that is why there are so many methods by which you can solve the recurrence relation. And if your recurrence relation is of this form, T of n is equivalent to ATN by B plus F of n. Like you have seen the recurrence relation for what? For merge sort, for binary search. If you remember for this, what was the recurrence relation for merge sort? If you remember, T of n is equivalent to 2T n by 2 plus, yes, it was of the order of n, big O of n. Yeah, simply you can write n, isn't it? Yes, this was it, 2T n by b plus of the order of n. So where this, I will explain how this is coming for the merge sort. Similarly, if you go with the binary search, that is also we can write. Like this is the equation for binary search. Let me write this as well. Later we will solve these. Let me type this as well. T of n is equivalent to T of n, but actually it is divide and conquer, if any one of you have the idea. So these are the two recurrences. See, both the recurrences are of this form, ATN by B plus F of n, where this A is greater or equal to 1 and B is greater than 1. Right? And and this function F of n can be any function. Right? See, now what is this n actually? N is the size of the problem which we are having. It is the size of the problem, this n. This is the size of the problem, this T of n. It is the size of the problem. For example, if you, like suppose you are performing a merge sort, right? And there are some elements in the list. You have to perform merge sort on this list. Then what is the size of the list? 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is equivalent to 9. Right? So n is simply what? The size of the problem. And what is A? A is the number of sub problems. See here. In the merge sort case, what is A? It is 2. Can anyone tell me why it is 2 in merge sort? Be quick with your answers. Can anyone tell me what is this 2 in case of merge sort? Yes. Great. It is simply we are actually using the master method, this divide and conquer method, and we are dividing the problem into two sub problems, right? So if you have a list of 10 elements, you are dividing the list into n by 2. So that is why this is A. A is the number of sub problems in the recursion. So you have got two sub problems in the recursion, right? Why here also, if you remember in binary search as well, you are also dividing the list into two, but why there is no 2T in this binary search? Can anyone? Why there is no 2T in binary search? Yeah. Why there is no 2T in binary search? Although there is 2T in merge sort. It will be already sorted, yes. Before searching, any answer? Anything else? Why there is no 2T? Great. Because whenever you have binary search, you are comparing your element which you have to find with the elements in the list. Once your element is found, you will traverse, you will search only one part of the array and remaining part will be excluded, right? That is why there is only one T in this recurrence relation of binary search, right? Because if you have, like, suppose you have to find an element in the list. Let me take an example like this. You have a list like this: 2, 5, 7, 9, 10, 56, 78, 90. So this is the list, like, suppose, and I just want you to find this element 56. What you will do? You will compare this 56 with the mid of the array. So, like, suppose 10. So once you find 56 is greater than 10, so you will search then only this part. So that is why we are going with only half part of this array. So that is why here it is 1. But here, whenever you are doing the sorting, it is actually dividing it, then using the pivot, doing first part, then second part as well. That is why it is 2, right? So this is A actually. A is the number of sub problems. Hope it is clear, right? Then we have got n by b. N by b is simply the size of each sub problem. Means once you have this list and you are dividing your problem into sub problems, like here also you have divided the sub problem 1, sub problem 2. Similarly, in this you are dividing the list. So this n by b, it is actually the size of each sub problem. Means here, if the list is of 10 elements, the sub problems will be 10 by 2. Similarly, if the list is of 100 elements, the first sub problem will be 100 by 2, and so on. So this is actually what is this A, what is this n, and what is this n by b. And f of n is simply what? Cost of the work done outside the array. Means whatever would be the other costs apart from the recursive calls. Once you have got so many recursive calls within that recursive function, so it could be other function. Means other costs that we are taking into consideration for this algorithm, right? Which includes the cost of dividing the problem, cost of merging the solutions to subproblems, etc., etc. So this can be anything apart from the recursive calls. It can be dividing cost, it can be merging cost, etc., etc. So this is actually what is master method. Hope it is clear. Yes. Please give me confirmation. Give a thumbs up if it is clear. See, this is actually the basics of these recurrence. Once it is clear, you can solve any recurrence relation of this form, and I will show you the best method. Not although best, but I will show you logically how to solve it. Okay, so this is actually, and you have to remember it. ATN by B plus f of n. T of n is equivalent to ATN by B plus f of n, where A is the number of sub problems, n is the problem size, and n by is the size of each sub problem, and f of n is the cost, or I can say the work done. Apart from the recursive calls, it can be like dividing cost, merging cost, etc. And value of A, because you know, when A is the the size of the problem, it should always be greater than 1, and B should be greater than 1. Kyun? Because it is n by b, and size of each sub problem, it has to be greater than 1. It should not be equal equal to 1, because if it is b, now n by b, it is the problem itself. N by b, it is equivalent to n itself, then that is the problem itself. It means we are not dividing the problem, so it has to be greater than 1. Always remember these things. Again, I am repeating. Logically, try to understand why b is not equal to, by b. What if b is equal to 1? क्या होगा when b is equal to 1? Yes. What if b is equivalent to 1? There is only one element. Yes, it is n itself, because when n by b is equivalent to b is equal to 1, so it would be n itself. So it would be problem itself. So there is no fun of dividing it. So that is why b has to be greater than 1. Okay, great. Great to see your answers. Okay, now how to solve these recurrence relations with the help of master method. See here. there are actually 3 cases. Be attentive for this session. Once you will learn it, you will solve the recurrence relation within 2 seconds. Right? So, but the thing is, you have to be very much attentive for these 10-20 minutes. We will be solving it, and it would be it would be you will solve it within on the fingertips. No need of any calculation, no need of any kind of a thing. Just remember the cases and you will solve the recurrence relation. And once you solve, you will have a very much grip over the algorithm analysis, over the performance analysis. Great. See, there are now 3 cases for this at n by b plus f of n for this recurrence relation. The very basic first case. See here, if f of n is of the order of n raised power log a to the base b minus epsilon. Remember this. Don't get like most of the time is what we usually see. We usually get frightened about these expressions. When we see this kind of an expression, we usually see no, it is kind of a rocket science. It is very easy. It is very basic mathematics. I will tell you. See, there are 2 functions over here. One is t of n, and another one is f of n. These 2 are important, and whole this master theorem revolves these 2 functions. Now the very first thing is we are just checking this f of n. If this f of n is of the order of n raised to the power log of, I'm just writing the base like this, base b. I'm writing like this because it is log a to the base b. It is log a to the base b, right? Let me write it like this. Log a to the base b. Let me write it like this. Okay. So we have to, whenever you are given any kind of a recurrence relation, you have to check for this f of n. If this f of n is this, of the order of n raised power log a to the base b minus epsilon. Now, you might be wondering what is this epsilon? Epsilon is simply a constant. For example, if you remember the previous recurrence relation, this one. See here. Here f of n is what? Order of n. Here f of n is simply a constant. So we will be computing here. Let me go directly to here. What is the value of a? Can anyone tell me what is the value of a? A is equal to 2. What is the value of b? It is also 2. Now, what is n raised power log a to the base b? Let me write using this pen. N raised power n power log of a to the base b. Can you calculate what is log a to the base b? Log 2 to the base 2. What is the value of log 2 to the base 2? Yes. What is log 2 to the base 2? Yes, it is 1. I will show you how to calculate it. It is simply 1. So what would be n raised power log a to the base 2? It would be n raised to the power 1. And we have to compute this n raised power 1 with this t of n. F of n. So here f of n is n, isn't it? And your n raised power log a to the base b is also n. I hope you are getting it. Isn't it? So here both are equal. But if this n raised power log a to the base b is greater, for example, if I had the case of like this, Let me say if my f of n is मान लो if it is n as it was, but my log a to the base b is greater than this. Like suppose it is not 1, it is 3. So n cube is n raised power log a to the base b, and f of n is n. So at this means what? This n cube, in order to make this n cube equal to n, I have to subtract some value from it, yani ki n minus 2. So this is actually epsilon. So whenever you are getting a case like this, then you will say the first case is applied. Let me repeat it again. Just remember the case. Then we will see. Example is easy. It is not that much difficult. Again, I am repeating. If your f of n is of the order of n raised power log a to the base b minus epsilon, then t of n is simply n raised power log a to the base b. For example, let us compute this. See, always remember when you are having a recurrence relation, first always try to find log a to the base b. Whatever would be the case, try to find log a to the base b. What would be here? Log a to the base b in this example. Yes, log of a to the base 2. What would be the value? Log of a to the base 2. Great, it is 3. And I hope you might be knowing it how to compute the log. It is a 1 second task. Great, it is 3. See here, I will show you. Whenever you have a log of this, log a to the base b, always see log a to the base b. It is simply, I will tell in basic terms, what could be the power of b so that we have to make it a. b को क्या पावर जाएगा a बनने के लिए. Like here 2 को क्या पावर जाएगा 8 बनने के लिए, तो 2 को पावर जाएगा 3. Similarly, if you have a log of let me write like this. If you have log of 64 to the base 2, can anyone tell me what is it? You don't have to, you don't need now calculator. 64 log to the base 2. Anyone? 2 को क्या पावर करेंगे? What could be the power of 2 so that it will be 64? Yes, simple. No need to perform any kind of a calculation. Simple. It is simply 6. So that is the basic way. Whenever you have any kind of a log, just check what could be the power to the base so that make it this value. It can be base 2, it can be base 10, but most of the times in computer science we will be dealing with base 2. Hope it is clear. Yes or no? Till now it is fine. Yes, is it fine till now? Great. See, so here in this case we found it is log a to the base b is 3. So t of this yes, f of n is order of n raised power log a to the base b minus epsilon, right? So here what is f of n here? F of n is n square, right? And t of n we have to find. So n square is f of n, and what is n raised power log a to the base b? It is n cube. So what does this mean? It means that we have to subtract something from n raised power log a to the base b from this term in order to make it n square. Isn't it? Here is the main crux is here. Again, I am repeating. Again, I am writing it. See here, we have two things. N power log a to the base b not able to write properly. It is n power log of a to the base b, and we have another function f of n. It is written, it is given in the question, and we found it to be n cube, and it is given in the question, it is n square. Now we have to compare. If this f of n is n raised power log a to the base b minus epsilon, right, for some constant, then we can say that first case is applied. If we check here, n power log a to the base b, it is n cube, and in order to make this n cube equal to n square, we have to subtract 1. So the first case is being applied. Whenever we are applying the first case, so at that time complexity is simply t of n is n raised power log a to the base b. So the complexity of this question would be what? It would be n cube. And at the end, I will tell you how to remember and how to make a decision. Simple. I hope it is clear. In order to make n square equal to n cube, it means we have to subtract some value. It is n raised power log a to the base b minus some epsilon, minus some constant. So when you are subtracting, when your value n raised power log a to the base b is bigger than this functional value, then it means the first case. Simply at that time, it is n raised power log a to the base b. Hope it is clear. So for this case, it is n cube. So the complexity would be n cube, of the order of n cube. Hope it is clear. Just give a thumbs up if it is clear. Yes, quickly. Just a thumbs up. Okay, fine. See, so this is the first case. Yes, now the second case. See, second case is simply if this f of n is theta of n raised power log a to the base b into log n, then it would be simply n raised power log a to the base b multiplied by log n. Forget about this care for the time being. It is nothing. Simply, if your f of n is simply n raised power log a to the base b into log n, then your complexity would be n raised power log a to the base b. Right? Okay, see here. This is the example. Let me put the cursor here. Okay. So the example is 2t n by 2 plus 10 of n. What is the value of a? It is 1. What is value of b? Here also it is 1. So what is n raised power log a to the base b? So it is n raised power log 1 to the base 1 is 1. So it is equivalent to, so f of n is also n if we see, and n raised power log a to the base b is also n. So both the cases are what? Both the cases are equal. When f of n and this t n raised power log a to the base b are equal, then at that time we simply multiply the function with log n. Always remember it. So it would be n raised power log n log a to the base b, n raised power 1 multiplied by log n. So that would be the complexity of this case. Hope it is clear. See, always, again I am repeating, always check with n raised power log a to the base b and f of n. If it is n raised power log a to the base b is greater, then simply that would be the complexity. If n raised power log a to the base b and f of n are equal, then multiply n raised power log a to the base b with log n. And in third case, if this n raised power log a to the base b is less than f of n, then the complexity is f of n. Very basic. Nothing to remember that much. Hope it is clear. Yes or no? Oh, sorry. Sorry, I actually. Sorry. I was about to click on this annotate. I guess I clicked on mute. Sorry. So may I know where from I have to repeat? Actually, I have to click on this annotation. I clicked on audio button. Sorry. From case 2. Okay. See here. Let me recap all the 3 cases and I will tell you how to do the thing. See, we have the main important thing is n raised to the power log of a to the base b. This one. Second thing is f of n. These things are important, right? See, always compare these two things. Whichever is bigger, that is the complexity. Now, if this is bigger, this is complexity. If f of n is bigger, this is complexity. If both are equal, then you have to simply multiply it by log n. Let us take the case. For example, let us take some reconciliation like suppose 16 t n by like suppose 2 plus n. Find the complexity of it. Second, I will write like 2, I will write this by merge sort 2t n by 2 plus n. Then I will write like 2t n by 2 plus n cube. What could be the complexity of this case? Yes. What could be the complexity of first case? Can anyone? See here. We will compute n raised power log a to the base b. What is n raised power log a to the base b here? In the first case, it would be equal to what? In the first case, it would be. Can anyone tell me in the first case what it could be? It would be simply n raised power log of 16 to the base 2. So that would be equivalent to n raised to the power 4. In first case, it would be n raised to the power 4. And what is f of n in the first case? It is n. F of n is equivalent to n. Which is bigger? Which is bigger? N or n raised power 4? So simply n raised power 4. So for this, the complexity would be of the order of n raised to the power 4. What about second case? It is n raised power log 2 to the base 2. So n raised power 1 and n raised power 1. So what could be the complexity? It would be of the order of, yes, n multiplied by log n. What about third case? It is actually n cube. It is n raised power 1 and n cube. Which one is bigger? The third one is bigger. So the complexity would be n cube. So this is actually how master theorem is without computing A, B, C, first case, second case, third case. Always try to remember, not remember, always try to find n, A, B, f of n and n raised power log a to the base b. Once you will clear all these things, everything will become clear. Hope it is clear. See, it is now you can find in a single click. In 20 seconds, you can compute the complexity of any recurrence relation. See, n log n is simple because in both here, when f of n and n raised power log a to the base b are same, then at that time you have to multiply any of the function with log n because it can be f of n or log n raised power log a to the base b. Both are equal. So whenever both these functions are equal, multiply the function with log n. Here, if you see, f of n is also n and n raised power log a to the base b is also n. So both f of n and n raised power log a 2 are equal. So then multiply this n with log n. That is simple. You will not find these kind of things anywhere. You have to logically think and come to the conclusion. Hope it is clear now. If you will not, if you can't understand it like this way, then it will become difficult. Then you have to go through all the steps, etc. Take 10-15 minutes or 2-3 minutes to solve the recurrence. But better is the way which I showed you. It is always the best, and it is giving the solution in 2-3 seconds only. Hope it is clear. Yes or no, please. Give a thumbs up if it is clear. Try to solve equations like you have merge sort, quick sort, binary search. Actually, merge sort and binary search I have shown. Try to, no, why half clear? Either it should be full or it should not be. Half is not the case. Again, I am repeating. See, finally, I will tell you what to do again one more time because it is important topic. That is why I am giving stress on this topic. See here, always try to find n raised to the power log of a to the base b. Once you found it, then find f of n. It is always in the function, right? Then what you will do? Then compare these two. Whichever is bigger, that is the complexity, right? If they are equal, then multiply the function by log n. So this is the crux, right? So whichever is bigger, that is the complexity. If they are equal, then multiply the function by log n, like in case of the binary search. Got it? So this n raised power log a to the base b minus epsilon is when n raised power log a to the base b is smaller. Similarly, n raised power log a to the base b plus epsilon is when f of n is smaller. So at that time you have to, but when you are solving the recurrence, only then you have to remember all the cases, all the steps. But when you are computing the complexity, just remember this, right? So when you are doing this, remember the steps, you will be done with the example. Someone is saying that Morris thought how it works. So it is simple, 2t n by t plus n. In that case also both cases are equal, n raised power 2 to the base 2, right? So n raised power 2 to the base 2 is n raised power 1. Also your function f of n is also 1. So both are equal, n and n. So at that time, when both the functions are equal, what you will do? Multiply the function with log n. So it would be n log n. That's it. Got it or not? So it is common for all the cases of recurrence relations of the form a t n by b plus f of n. We have not done only Morris sort. We have done the case of binary search. We have done the case of 16t n by 4 plus n square. You can done 8t n by 2 plus n cube. Any recurrence relation of the form of a t n by b plus f of n. Whenever you have a case of that kind, use recurrence relation, use master form. Fine. If it is clear, just give a thumbs up, then we'll go forward. Try to solve multiple examples. Once you are done with 2-3 examples, it will become very much clear. Then you don't have to remember anything. You don't have to do any kind of a calculation. Just think of any problem, compute n raised power log a to the base b, compare with f of n, whichever is bigger, type the complexity. If both are equal, multiply by log n. That's it. If you got it, see, same concept is taking days to get clear, and still at the end of the day, we are not able to write a correct solution. But if you have remembered it, I have put it in very much simpler words after checking, after discovering from multiple sources what could be there. There are some exceptions to it as well that we'll cover later. But one, if you have got it, you can compute any complexity. Okay, just give a thumbs up if it is clear. You can take a screenshot of this writing as well that I have written. It's a kind of an algorithm that I have written over here. Okay, great. Now we'll see. Okay, third case done. Yeah, there are some exceptions to it where master method cannot be applied. Can anyone tell me? I guess I have written the reasons as well. See, if you are, let me cover it. Can anyone tell me why master method cannot be applied to this case? First case. Yes. Why master method cannot be? Binary search is simple. See, what is the recurrence relation for binary search? For binary search, recurrence relation is simply tn by 2 plus 1. So a is 1, b is 2, f of n is 1. When a is 1, b is 2. What is n raised power 1? N raised power log a to the base b. यानी कि log 1 to the base 2. So it would be 0. Isn't it? So n raised power 0. What is n raised power 0? It is 1. And what is f of n? F of n is also 1. Both are equal. So what could be the complexity? It is 1 multiplied by log n. So that is why we are coming up with what? We are coming up with log n. Got it? Yes or no? Okay. So the question was here. Why first case, why cannot be applied? Because a is 2 raised power n. So because it is not a constant, that is why master method cannot be applied. Here also, master method cannot be applied because there is a non-polynomial difference between f of n and n raised power log a to the base b. If we check, f of n is this, and what is n raised power log a to the base b? It is n raised power 1. So there is non-polynomial difference. Similarly, here a cannot be 0.1. So a is less than 1. So we cannot have less than one sub problem, right? So the sub problem has to be 1 or more than 1. Similarly, in this case, f of n is negative. So what does that mean? F of n is negative. If you know, I have told you that f of n is actually a work done. For example, it can be a work done in dividing the subproblem, in merging the subproblem. So work done cannot be negative. So that is why this f of n cannot be negative. When f of n is negative, so it means master method cannot be applied, right? Similarly, over here, the function is like this. So that is why there is not any polynomial kind of a difference between f of n and n raised power log a to the base b. I hope it is clear. Great. If it is fine, then we will take a 5-minute, 10-minute break. Then we will come back and we will check what we will do next. Hope Master Thomas, then I will tell you this Tower of Hanoi in last 20 minutes. If you have any questions, please ask. Yes. Any question, please ask for like 5 minutes, then we will go for a break. Yes. No questions. Slide of reconciliation structure. I guess we have done that. So this was the recurrence relation. And we have discussed recurrence relations as well. We discussed recurrence relations. A relation or a mathematical expression in which n term is represented in terms of its previous term. That we discussed. We discussed Fibonacci, we discussed factorial, we discussed Tower of Hanoi, Tower of Hanoi, not yet. Then we discussed. Okay, if you want to take a snapshot, you can take. No problem, I will share. See, master thumb is simply a thumb or a method which is used to solve a recurrence relation of the form ATN by B plus F of n. These recurrences are solved with the help of master thumb. And you have seen so many recurrences we solve, like ATN by B plus F of n. It can be 2TN by B plus n for merge sort. It can be TN by 2 plus 1 for binary search. It can be any 8TN by 4, 16TN by 4, any. So that is the master thumb. Simply a master thumb is a method or a master method used to solve recurrences of this form. And in that we have got 3 cases. N raised power log a to the base b plus epsilon minus epsilon, and when both the cases are equal. There are some exceptions, don't bother about that, that will not be asked. Okay, anything else? Yes. Anything? Anything else? Okay, so there are no more questions. We'll go for a 10-minute break. So it is 2016. So we'll be back at 2025. Okay, so 8-minute break we'll be taking. Okay, welcome back. Hope I am audible. Yes, am I audible? Okay, fine. See, now we'll see something about recurrence. Yes, Tower of Hanoi. And you might be knowing what Tower of Hanoi is. Yes or no? It is actually towers of Okay, see, actually, this Tower of Hanoi, it is more related to recursion, right? That is why I want to discuss it over here. It was initially, I guess, invented by a French mathematician, right? So, I guess it is more related to Greek problem, ancient Greeks. So they were just having some 64 discs. They were having 3 towers. Let me annotate it. So 3 towers were there, or they were calling it sometimes pegs. So as per their ancient Greeks problem, so they were saying that we have got 64 discs. On this tower A, and so on. They just want to shift these discs from tower A to tower B using tower C. But there are some conditions for this. The condition was that only one disk at a time, one disk at a time can be moved. And the second condition was, can anyone tell me? The bigger disk cannot be placed on the smaller disk. So these are the two conditions. So the ancient Greeks thought that once, because at that time now the discs were, as it is as per the history, the discs were so heavy that they were just it was taking so much long time to move a disc from one tower to another tower. And one more thing, that the condition two is only one disc at a time, because the discs were very heavy and bigger disc cannot be placed on a smaller disc. So these were the two conditions, and ancient Greeks thought that the world would come to an end once we will move all the 64 discs from tower A to tower B using tower C. So it was the problem of ancient Greeks, although it was invented by a French mathematician. Right? Now we have to find the solution of this problem. Hope it is clear. I discuss again. I am repeating. See, we have 3 towers. Tower of Hanoi is a Greek problem. It was invented by French mathematician. We have got 3 towers: tower A, B, and C, or we call them as pegs: peg A, peg B, and peg C. We have got some discs. Initially, it is believed that there were 64 discs on tower A, and the problem is we have to move these discs from one tower to another tower using the third tower, or I can say tower A to tower B using the tower C. But there are two conditions that we have to meet, that we have to keep into consideration. Only one disk at a time can be moved, and the second condition is that the bigger disk cannot be placed on the smaller disk. So this was the problem, Tower of Hanoi. Now we have to solve it. If you remember, I have written a recurrence relation for this Tower of Hanoi. Can anyone tell me what was that recurrence relation? See, it was h of n. What was this equivalent to? Recurrence relation, because it is a recursive problem. It is making use of recursion. So I have to write a recurrence relation. It is twice h of n minus 1 plus 1. Can anyone explain why is it so? Why is it like this? Twice h of n minus 1. Yes. Any guesses? Why is it like this? Any guesses? Okay. Let me tell you. Be attentive. See, simple. Nothing kind of a rocket science. Initially, what we are doing, we are actually moving top n minus 1 disks from one tower to another tower. So the steps are h of n minus 1. Fine. Then the remaining one disk, this one, I will be placing over here. So plus 1. Here it would be plus 1. H of n1, n minus 1 plus 1. Then the remaining n minus 1 disks that are on this tower, isn't it? That I have moved over here, this bunch. I have placed it like suppose here. Then I have to move them back here. So again, how many steps? It is again plus h of n minus 1 steps. So in total, what we are getting? We are getting in total twice h of, if we add them up, it is simply twice h of n minus 1 plus 1. So this is the recurrence relation for tower of Hanoi that I have written. Now how to solve it? It is solved using the iterative method. I'm not going to solve it over here. It is simple. Simply we have to write 2 twice hn minus 2 plus 1 plus 1. Then again it would be 2 into 2 hn minus 3 plus 3. So whenever we solve it, we'll come up with a solution. Can anyone tell me what is the solution of the recurrence relation? Yes. Is it clear? Just tell me, give a thumbs up if it is clear. Tower of Hanoi. I'm not getting any kind of responses from you. Is TOH clear? Is it clear? Just give responses in the chat box. And how the recurrence relation is twice hn minus 1 plus 1. I guess it is also clear. Type in the chat box if it is fine. If you want me to repeat it, I will repeat. It is simple, not that much difficult. See, Tower of Hanoi, we have got 3 towers. Tower A, Tower B, Tower C. We have discs. We have to move these discs from Tower A to Tower B using the third tower. Right? So there are 2 conditions for it. Only one disc at a time and no bigger disc on the smaller disc. So it was a ancient Greeks thought that world will come to an end if we move all the 64 discs from Tower A to Tower B using the Tower C. Now we have created a recurrence relation for this Tower of Hanoi. That is simply twice hn minus 1 plus 1. So how it came, I have shown you. Because initially what we are doing, we are moving top n minus 1 discs from Tower A to Tower B. That is hn minus 1 steps. Then there is one more disk at the bottom. I am moving that disk, means plus 1. Then again from tower B, the top h1 minus disk, I have to move back to the tower C, means the original tower in which for which I have to make a shift. So for that also we have to perform hn minus 1 steps. In total it is twice hn minus 1 plus 1. Hope it is clear. Can anyone tell me, when we solve this recurrence relation, what is the solution of this recurrence relation? What is the solution of this recurrence relation? Twice hn minus 1 plus 1. It is simply, okay, let me not ask you, let me not tell you for the time being. I'm just waiting for your answers. What is the solution for this recurrence relation? Can anyone? Okay, let us do an exercise. Like suppose I have two disks. What would be the number of moves in moving these two disks from tower A to tower B using tower C? I have two disks. This yellow, this. One disk, two disks. What would be the number of steps? First I will move one here, then two here. Then I will move one here. So it would be 3 steps. Isn't it? What if I have got 3 disks? What would be the number of steps? What would be the number of steps for 3 disks? Yes. What would be the number of steps for 3 disks? Quickly. You can do it. I'm waiting for your answers. What would be the number of steps for 3 disks? 7 moves. Great. Who is saying 3? It is not possible. 4 is not possible also. It is 7 moves. And I will tell you how. Let me share this screen. Hope my screen is visible. See here. Hope my screen is visible. Is my screen visible? Yes. Okay, see here. I will be moving here. 1 step, 2 step. I will move this back here. Sorry, just a minute. See here. First I will move this here. 1 step. Then this, 2 steps. Then I will move here. 3 steps. I will move this here. 4 steps. 5, 6, and 7. So there are 7 moves by which I push 3 disks from this tower to this tower. Right? What if I will increase the number of moves? See here. First this, then this will be there, this will be there, this will go there. 8th move, 9, this will go there, this will go there, then this one, then this one, then this one, then this one. So in total for 4 disks I have got how many moves? 15 moves. Can anyone tell me for 5 disks what would be the number of moves? Yes, for 5 disks what would be the number of moves? What would be the number of moves for 5 days? Yes, it would be 31. If we check, see here, how it will be solved. And what is the solution of the recurrence relation for this? Simply the solution would be, it would be 2 raised to the power n minus 1. That is, if you have got 5 days, so what would be the number of steps? It would be 2 raised to the power 5 minus 1. That is 32 minus 1 is 31. Similarly, if you have got 8 disks, So what would be the number of steps for a disk? So it would be 2 raised to the power 8 minus 1. And what is the solution? 2 power 8 minus 1? Can anyone tell me what would be the number of steps for a disk? Yes. Great. It is 255. So imagine what would be 2 raised to the power 16 minus 1. It is a big number. So that is why ancient Greeks told that the world would came to an end if we move all those disks from peg 1 to peg 2nd. It is a big number, 2 raised power 16 minus 1. If you check it, it is, if I will check it, two raised to the power 16 minus 1. It is a very big number. Six five five something like that. Yes, 65536. So this is Tower of Hanoi and how we solve this Tower of Hanoi. Hope it is clear. Yes or no? Yes, please. Okay, so with this, I guess we completed the basic performance analysis portion. And we covered algorithms, asymptotic notation, recurrence relation, and now this Tower of Hanoi kind of a thing. If you have any questions till now, please ask questions. Then we will cover the basic Java object-oriented portion. Yes, if you have any questions till now, please ask. Okay, this was a very important portion related to algorithm design, or I can say this DSA portion. Because once you have this portion clear, you can compute the complexity of any algorithm, and you know it very well. These complexities are being asked in every exam. So you have to revise the concepts of performance analysis, algorithm design, recurrence relation. So you have to revise this. Whatever we discussed since day one, kindly rewind it and keep a thorough understanding of these concepts. Like what is performance analysis, what is time complexity, how do we compute time complexity, what is space complexity, what are asymptotic notations, different types of functions, how is this not growth related to those functions, how functions are varying. We have to arrange those functions based on their this not growth, which function is bigger, which is smaller, and so on and so forth. So you have to check all those kind of things. Then today we discuss something about this. This now right now we discuss Tower of Hanoi. So I guess it was not that much difficult. We covered it. Okay, let me share another screen. Okay, hope the screen is visible to you. Yes. Is screen visible? Just a confirmation. Great. Okay, so now we'll be doing what? We'll be understanding the basic concepts of Java, and you might be knowing it very well that Java is OOPS concept. It is an object-oriented programming. OOPS, right? So we'll be having a brush up of the basic concepts of this Java. See, these are the concepts that we'll be covering in these slides. I guess it is not possible to cover whole slide today. So whatever would be like whatever will be covered. So that would be all in these from these concepts like object, class, data abstraction, encapsulation, so on and so forth. See, Java, it was initially developed by James Gosling at Sun Microsystems, and it was first released in 1995. So this is something about the history of Java. Yeah. Now, what is object-oriented programming? See, we have got multiple kinds of programming. You have got procedural-oriented, you have got object-oriented. As you know, Java is object-oriented programming. Now, what is object-oriented programming? It is a modern programming that is used to design a program using classes and objects. Like in other programming language, the more concern, the more focus is on data. But in OOPS, we most of the times focus on classes and objects. So it is a modern programming method that is used to design a program using classes and objects. Now, there is a question, what is a class and what is an object? Right? See, it is simple. Class is simply a basic, or I can say a blueprint or prototype from the objects which we are creating. Like we are creating multiple objects in object-oriented programming. And this class is actually a blueprint or a prototype from what objects we are creating. Simple. And what is this object? Object is simply a real world entity that has got its name, that has got some properties or kind of a behavior. For example, you can have an object of kind book, you can have an object of kind chair, you can have an object of kind car, pen, table, etc., etc. Simply we can say they are real world entities. It can be a person, it can be a car, it can be table, etc., etc. Now these are objects. So class is actually a blueprint of this object that we are creating. For example, car. Car is an object. So you can have the property of a car, right? You can have, I can say this color of a car. You can have size of a car. So they are actually real world entities. For example, see, these are objects. These are the properties, and this is the behavior of, like, suppose if it is a car, start, stop, forward, backward, and these are objects. Right? Okay. Now, what is the difference between procedural versus object-oriented programming? As I already told you, in procedural, this object-oriented programming, we are dealing with objects and classes. And this POP, procedural-oriented programming, it is known as POP. It follows top-down approach. May anyone know what is top-down and bottom-up approach in programming? Yes, can anyone tell me what is top-down and bottom-up approach in programming? Yes. Can anyone define top-down? Yes. Great. See, it is simple. Great to see your answers. Thank you so much. When we have top-down approach, it starts from the higher level. Means we start with a high-level overview, and then we break down the problem into smaller, or I can say more manageable parts. While if you have got this bottom-up approach, it builds the problem from smaller problems, or I can say that from the ground. And it is most of the time this bottom-up is focusing on what? Components. Then we are integrating, combining those components into large system. Simple. Bottom up means from scratch, from smaller problems to bigger problem. Then this top down means we are dividing this bigger problem into smaller problems. Smaller to bigger, bigger to smaller. Top down and bottom up. So this POP, procedural oriented programming, it is top down, means from a bigger problem we are dividing that bigger problem into smaller problems. Then And one more thing, this POP, procedural oriented programming. You might have studied so many procedural oriented programming, like it is C, Fortran, etc., etc. There we deal with algorithms, right? And these POPs are divided into functions. It requires less memory, and it does not have access these modifiers. And one more thing about this POP is that data can move freely from one function to another function in the system. And very important drawback of these POPs is they are less secure. For example, you can have C and Fortran. But in case of these OOPS, object-oriented programming, it follows the bottom-up approach. Right? Means we are starting with smaller problems, then we are building them into bigger problems. Means finding the solution. It deals with data. That was dealing with algorithms, right? It is dealing with data, and we are this OOPS. It is divided into objects, and at the same time, it is needing more memory than POP, than procedural oriented programming, right? It has access to access modifiers. Okay, just a minute. Someone has a no. Okay, you are just writing it. Okay. Here objects can communicate with each other. Their data, we were communicating through functions, from function to function. Here objects can move and communicate with each other. Here also we are having functions, but there are special kind of functions in OOP. We call them as member functions. So these objects can move and communicate with each other through these member functions, and it is more secure than POP. The example of object-oriented programming, you might be knowing it. It is C++, Java, C#, etc., etc. So this is the basic difference between procedural and object-oriented programming. Yeah, there are some these now OOPS features, OOPS paradigm features. Here, as I already told you, this is the more emphasized is on data rather than procedure, because in procedures more emphasis is on algorithm procedures, but here we most of the times or mostly we emphasize on data rather than procedures. Here the programs are divided into what are known as objects, because we are dividing the program into objects, and in this object oriented paradigm we are creating data structures in such a way they categorize the objects. Means whatever you are creating, whenever you are creating a data structure, they are designed, they are created in such a way that they categorize the objects, right? So we have to categorize the objects based on the data structures that we are creating. And here also the methods that operate on the data of an object are tied together in the data. You might have learned about it: encapsulation, late binding, etc., etc. So here actually these objects are tied together in a data structure. And one more feature of this paradigm is that data is hidden. That is why we told in the previous slide that it is more secure. So external functions cannot access the data. And later we will see there are private functions, public functions, etc., etc. So the outside functions, or I can say the external functions, they cannot be given the access to check the data. So that is why we say data is hidden. And here data, or I can say to be more precise, the objects in OOPS, they communicate with each other through methods. So here we have got certain special kind of methods by which the objects can communicate with each other. And here one more feature is that new data and methods can be easily added whenever necessary. Whenever you have to add any method or any kind of a data, we can add that. As already discussed, it follows bottom-up approach. The individual base elements of the program are specified first. Then we link them together to form large subsystem. Means from a basic problem, we are creating the solutions for, or I can say the larger subsystems. Then there are some applications of this OOP. The very basic is we can create real-time systems. We can simulate the model, or I can say simulation kind of a thing we can do. We can perform modeling. You can have object-oriented databases, hypertext, hypermedia AI and expert systems can be created with the help of OOPS. Neural networks, parallel program, decision support, office automation systems. So all are the application of OOPS. Means you can create these kind of systems with the help of OOPS. Right? So this is something about OOPS. Now what is Java? Java is, as we discussed, Java is an OOPS language. Simply, or I can say C++ as well. C, Fortran, they are what? Procedure oriented. Right? So what is Java? Java is simply a computing platform for application development, and it is an object oriented language. So whenever you have to create any kind of an application, you can make use of Java. It is class based, and it is a concurrent programming language. Means by concurrent we can mean that many statements can be executed at the same time instead of sequentially executing. Means you cannot we can execute all the statements all together instead of executing one, then another, then another, then another. You can execute all the statements, many statements at the same time instead of sequentially executing them. That is what we call as concurrent programming language. So one more thing about Java is that it can run on all platforms, and it has got free access. It is free to access. It is platform independent. You know it very well. It is simple, secure, robust, and it is a totally full pack, I can say, complete object oriented programming, and it is platform independent high level language. You might be knowing it. I've got multiple kind of computer languages. You have got high level, low level, etc., etc., machine level languages, but this Java is high level language. It is platform independent, and it is a complete object oriented program. It is also portable. Multi-thread technology gives high performance to Java. It supports concurrency, means the code that we are using, or that by which we are writing a program, that can be executed by multiple processors at the same time. Means it is following the concept of concurrency that we have in operating system. So the Java code can be executed by multiple processes at the same time. How it works? Simple. You have a program, source file, right? Program.java. We give it to our Java compiler. The compiler converts that source code into bytecode. Then we have a output at the Java program. Simply, if you see here, we have a program. We give our program to compiler. Then there is a Java virtual machine, JVM we call that. Then we are getting the output. See here, this is the process of compilation. You have a Java program. We call that as a source code. Source code gets converted into bytecode with the help of this Java compiler, right? Then this bytecode gets converted into machine code, real machine code, with the help of this Java interpreter. And you might be knowing the difference between compiler and interpreter, that you will check again. So Java program, we have a source code, we get that gets converted into bytecode with the help of compiler. Then bytecode gets converted into the machine code, real machine, with the help of interpreter, right? Compiler is executing the program like this, whole at a time. It is doing line by line, that you might be knowing well. Yes, OOPS concepts. I guess we are running short of time, so today we'll continue from this slide. If you have any questions, you can ask. Yes. Yeah, what is class? What is object? We'll be explaining it all. Yes. If you have any questions, you can ask. See, class is simply, as I already told you, it is a kind of a blueprint or a template that defines the structure and behavior of the group of objects. If you have multiple objects, right? The object can be a person, it can be car, it can be anything, right? So you have got so many attributes of that object. So that is class. Now, what is robust? Robust means simply na, like suppose if there is something, or I can say a language, that it has got the ability, I can say like this. If there is a language, Java is a language, it has got the ability to handle unexpected errors, I can say, or I can say handle errors, or there might be some unexpected situation. When the language has got this ability to handle errors and these kind of unexpected situations, we can say it is robust. So Java is a robust language, right? That is robust. Yes, robust is strong, very powerful. Yes, strong, very powerful. We can say it has got the ability to handle errors, right? Or if they are untoward or any unexpected situation occurs, we can say it is robust. It can handle that situation. See, compilation is simple. You have got a program. The program is given to the compiler. The compiler converts that program into bytecode. Then that bytecode is given to the interpreter, and interpreter is actually converting that bytecode into the machine readable format, into the machine code, ready to the machine. Simple. Compilation is simply what? Converting the source code, the program that you are writing on the like suppose that any text editor. When this program source code gets converted into the bytecode, we call that as compilation. Yes. Anything else? Anything? Any questions related to previous or this portion? Tomorrow we'll see the attributes or the properties of OOPs. Then we'll go one by one. Yeah, any questions? Okay, I guess there are no questions, so maybe we'll be winding up the session over here. What is distributed in buzzwords? Maybe may you be more clear about this question? See, distributed, it has got so many meanings related to multiple contexts. If we say we have got distributed systems, or we have got centralized system and distributed system, and this distributed, it simply means kind of an application where you have got a system, right? In distributed there are multiple systems, right? And at multiple, I can say, locations, they are dispersed from one another, but they still interact with each other, like kind of a distributed kind of a thing. You have got some mechanism, some system. If that system is working, but not at a single point, but it has got multiple sub points, and those sub points are at multiple locations. They are managed by a central location, and still they are interacting with each other. I don't know what you are saying about this distributed in buzz words. But distributed, I can say the system is distributed. System has got multiple components. They are geographically divided, geographically at multiple locations, but they still interact with each other. Okay, someone is saying that why. See, actually, whenever Java is compiling the program, it is making use of both compiler as well as an interpreter, because this I can say this Java compilation. It is actually a two-step process. The very first step is the Java, this compiler, it first converts this source code into the bytecode, which is then executed by Java Virtual Machine, JVM. And that JVM is actually acting as an interpreter. And with the help of that interpreter, this bytecode gets converted into the machine readable form. Right? Actually, it is a two-step process. One is first this bytecode gets converted into the source code gets converted into bytecode, then bytecode gets converted into the machine readable form with the help of interpreter. It is actually two-step process. Okay, anything else? Anything else? Okay, thank you so much. Thank you so much.
Yeah, thank you, sir. Thank you so much. We'll wind up for the day.
Okay, thank you.
Yeah. Yes, students. So we will meet again by tomorrow at 7 p.m. Thank you all for joining. Good night.